Okay, today we're going to look at another tutorial using ANSYS. Today we're going to model on a combustion process. We will look at the chemical species transport and what happened to the gas in the combustion. Okay, so today we're going to look at the combustion process of methane or CH4 in an air. Okay, today we're going to be using a model, a chemical model, which is involve an eddy dissipation model to simulate the combustion process. So we're going to look at what happened to the methane chemical in the combustion process. So later on, we'll look at the following point. We will do the normal setting for material properties, and we will set the boundary condition based on the next slides, right? So and then we will check the reaction of the flow in the graphic form, and then we're going to predict the thermal and prompt NOx production in this combustion process, and then we're going to compute the NO parts per million in our results. So this basically is a combination of a chemical process and also application in combustion. So let's say we have a scenario in this case. So we are simulating a cylinder combustor. So this one we break into half. So this is the center line of the combustor. So combustor, we have two inlet here. So here you have two arrows here. We will have an inlet for the methane or for the fuel, methane or CO4, and we have an inlet from the air. So there's a mixture of air and methane in this region. And the length of the combustor is 1.8 meter, and the height or the radius of the combustor will be 0.225 meter, and we have a wall in this section. Okay, and the information you can read from here. So we will we have all the parameter here. So the air will come in 0.5 meter per second at this temperature, and the methane or CO4 come in into this small inlet here will be 18 meter per second at a 300 Kelvin, and the radius of this inlet here for methane will be 0.005 meter. So later we will have two inlet over here. One is for air, one is for our fuel or methane over here. And then we have one outlet. Later we'll define this section as pressure outlet. Right. So before you simulate any model, at least you know what is your simulation domain about. And information given here is that the overall equivalence ratio is about 0.76, or we can say that we have 28% of air. The high-speed methane jet initially expand with a little interference from the outer wall and retain and mix with the low-speed air. The Reynolds number we use for, in this case, is based on the methane jet diameter, will be about 5,700. Yeah, the Reynolds number that we use for this methane jet over here, this section here will be 5,700. So this is our scenario. So we will use the ANSYS to simulate this scenario. So we'll see what happened to the combustion process of CO4 in the air, and then we'll see the chemical process. What are the species of chemical that will generate in this combustion process? So this is the chemical reaction that we'll use in our simulation. So in our inlet, we have two inlet. One is for our fuel, methane, CO4, and we have another inlet with air. So our air is CO2, is our oxygen. So when you combine your methane and oxygen, you will get carbon dioxide, CO2, and water. So later we will look at these four chemical species: CO4, oxygen, carbon dioxide, and water. Okay, yeah. Again, for this tutorial, we're going to use eddy dissipation model for the combustion process. This equation is achieve a state called stoichiometric state, a stable state, right? And let's jump into the equation, the simulation. All right, so first you need to go to the Moodle platform and go ahead and look for ANSYS file for species transport or gaseous combustion. The file, you click the file link, it will link you to the download site. You will be downloading this file, gascom.mesh file. So you need this file to generate, yeah. Okay, let's jump to our ANSYS, and I will show you how to simulate our combustor in this case. So in this process, we're going to our fluent here. We double click the fluent. So inside here, you save as maybe you save as species transport as a projects, and then go to the file and save the project so that you will save as okay, so we will save our project as species transport simulation as our workbench project file. You can name it anything as long as you're able to extract the file later on. Okay, so we are ready. So you double click the setup. You call it the fluent. In this case, because if you look at the combustor here, we are having a symmetry, a cylindrical object, so we can cut into half and then we'll run it in a 2D scenario. So let's back to our ANSYS here, our fluent setup here. So we are going to select 2D, and we're going to use double precision in this case, and we're going to use serial processing option. Click OK. So it will link you to the Fluent Solver machine here. So so far there's no mesh file over here. We need to import the mesh file. So go to File and import the mesh file. So after you download the file, you will get gascom.msh, the mesh file, gas combustion mesh file. So click this one, click OK. So you will get a file on the window here with a mesh file. So you can zoom in and zoom out. So we have a wall here, not wall, our symmetry plane here, and our inlet here, a wall. The white color is our wall. And if you're not sure what is it in our, you see, if you expand the boundary condition here, you see ID4, ID9, ID5, ID6, 8, 2, 7 here. You can go here, go to this window and right click. You will see a circle come here. So you will see the information come out from the console. So for example, this location is ID number 2. So ID number 2, if you refer to the boundary condition here, it will refer to wall ID number 2 is wall 2. So we're going to do setup later on. And then let's click some boundary condition. So here, here is ID number 4. It refers to interior. And then if you zoom in a little bit, you have inlet for your methane or CO4 will come in here, air will come in here. So if you click here, so this is your velocity inlet number 6, ID 6. If you look at the console, the ID 6 is here. So you have ID 6 is for your methane, and you click this one, you refer to ID number 8, which is refer to your air inlet here. Yeah, and if you zoom in, zoom out, and then you click here, the red color line here, you'll tell that this is zone number 9, or ID number 9 is pressure outlet here. So these are the few reasons that we will go through when we need to set up the boundary condition later on. Okay. All right. Now, the next steps after you have a mesh file, we will always go and check the mesh file. So go to the mesh setup domain here, mesh, click the check here. So the information will come out in the console here. And what is the most important data when you want to check the mesh is make sure you go to console and go to volume statistic here. Look for minimum volume here, and the number here is a positive value. Yeah, the number here is positive value. If you get the negative volume, means you need to redo the mesh, right? The mesh file have some problem there. All right. Then because this file, we need to set up this file. We need to scale this file into unit of mm. As you can see here is in meter. So we need to scale our drawing according to the unit that we use in meter. So this file was created in mm. So we need to make sure that we scale this file correctly. So what you do, you go to setup domain, mesh, and scale. So this scale mesh will come out. So before you do anything, you will see 1800 meter and 125 meter. So this one will is, if you look at the diagram from the screen here, the length is 1.8 meter. So if you convert in mm, it will be 1800 mm. Here you will be 225 mm. However, if you look at this file, the unit here is meter, so it's wrong unit if you do not do the scaling. So we need to do the scaling to convert this mesh file into meter unit, right? So we need to convert this dimension in mm into meter. So how we're going to do it? We will tell the computer the mesh file was created in mm. So go and select mm. After that, the view length, we use the unit SI, which is in meter. Then after that, you click scale. So you see, when you click the scale, the dimension will come to X max, which is here to here, will be 1.8 meter. And the Y from here to here will be 0.225, which is meeting our dimension in our problem here. So 1.8 for your X, 0.225 for your Y here. Okay, let's continue with our simulation. So once you click, once the dimension is correct, click close. And every time you scale something or you already manipulate the mesh file, either you scale it, you convert it to polyhedral, you merge it, or you separate it, or you fuse it, or you add zone to it, or you have a smooth or swap mesh after the process. Remember to go and check the mesh again. So go to mesh and then check again. So you will see that the volume statistic here important. Go and check the minimum volume, make sure it is a positive value. Okay. The next one, we will tell the computer that this mesh is simulated in asymmetric 2D space. It's not a planar, but in this case, we're going to simulate in asymmetric space. So highlight, you go to general, setup general, and then you will see this presentation or this window. If you're using a more latest version, you will see the similar presentation. So asymmetrics here. After that, going to the next step, we go to model, right? We're going to activate, or you can go to setup physics here, it will be the same. You can go here and click the activate the energy equation. If you click here, you will see that the energy will turn to on. Okay, it will move both way. Yeah, so click the energy, or you can come here and on the energy. Same. After that, we're going to use the K epsilon's turbulence model. So go here, viscous, right click, edit, and then we're going to use K epsilon turbulence model. Okay, And then we're going to use the standard K epsilon model. Near wall treatment, we use a standard wall treatment function. The rest, we use the default value over here. Okay, once we're done for the viscous model, click OK. So over your model, you will see energy equation was on. And for the viscous, we have the standard epsilon, and we are using a standard wall function for our model. Then after that, because we are going to analyze our species of chemical products in our combustion. So we're going to go ahead and we need to activate the species here. All right, so go to species and then right click, edit. So the species model will come out. We're going to use species transport. So we're going to transport we're going to see the transportation of our chemical products from left to right. So we're going to see, we're going to use a model called species transport in our case. So activate species transport. And then we're going to reaction. We're going to activate the volumetrics reaction. So as you can see, the more you click, the more presentation, more detail that you can do setting. And then you go to mixture property here. We're going to change the mixture material to methane air. Let me find it, methane air. Because our mixture is from between the methane and air. Of course, depending on your industry needs or operation, there are some standard library here that you can select, either diesel air or gasoline air and so on. So for your, maybe for your assignment, we will change the mixture material here for the combustion investigation. So remember where to find the mixture material. In this case, because our material is only methane and air, so we will simulate methane and air. After that, you'll be using a turbulent chemistry interaction using eddy dissipation model. So activate the eddy dissipation model in this case. Yeah. So eddy dissipation model, it will compute the rate of reaction under assumption that chemical kinetics are fast compared to the rate at which the reactant are mixed by turbulent fluctuation or eddies. Okay, I repeat again. For eddy dissipation, it will compute the rate of reaction under the assumption that chemical kinetics, they are faster or faster compared to the rate at which reactant are mixed by the turbulence fluctuation or eddies. All right, then after we specify our species model here, we will click OK. So in your console here, you'll see some warning. Here it say that it appears that the symmetry zone 5 should actually be an axis. So later on, we will correct this warning here in later steps. We will change the symmetry into axis later on. Okay, so we will solve this one in the next steps. Yeah. So after we define the model, we will go to material. So expand the material and then go to mixture here. So under mixture, you will see a methane air. Right click, edit. So methane air material will come out. Yeah. So in this case, we will look at the property methane air mixture species, the name here, you click edit this one. So the species window will come out, right? The species window will come out. Now in the library, you will see that you already generated the species that when you mix methane and air, you will see that there's a species of CO4, O2, CO2, water, and nitrogen. Yeah. So in this case, we will use the default species that are going to generate in the combustion process. Yeah. So then click OK. Then after that, we will, after you check the species, right? Just now you click edit, right? Then you go into check the reaction. reaction, we use eddy dissipation model. You click edit. So the reaction here, you will see that all the setting for the reaction using eddy dissipation. Eddy dissipation reaction models, it will ignore the chemical kinetics, or you can see the name here is Arrhenius rate. Here is a chemical kinetic calculation. And it will use only parameter in the mixing rate group here, right? So here, right? So mixing group, you have A and B here. Okay. Then after that, we will use all the default value in this window here. After that, we'll click OK. So after we have defined our mixture species, we have defined the reaction of our eddy dissipation model. And then you can check the value for your CP. For CP, we'll use the mixing law, and thermal conductivity, we use the constant value given over here. So same with the viscosity and mass diffusivity, we'll use the constant value over here. All right. Then after that, we're going to click the change or correct button. And then we close this window. So we have already defined the mixture property for our material in our combustor over here. Then after that, we're going to set up our boundary condition. So we close our material and then go to boundary condition. So all the boundary condition here will be referring to our diagram. Okay, our diagram. So our diagram here, we will define all this air, methane, speed, temperature in our boundary layer. Okay, so we go to the first one. We go to boundary condition. We go to symmetry plane number 5 here with this ID number 5. Click here. You go to boundary condition, double click, and then you will see that you can do selection. So go here, double click, then this text page will come out. Select symmetry 5. And remember that in the console, we see there's an error here. He remind us that symmetry 5 should actually be an axis. So we come symmetry 5 here, go to type here. We change it to axis. Change it to axis, like that. So after you change it to axis, it will ask you to rename the axis. So we will retain this name, then click OK. Once we done the symmetry number 5, we change it to axis already. We continue and define our inlet for air. So our inlet for air, just now I will show you, is velocity inlet number 8 here. Or you expand here is ID number 8 here. Then you go to edit. So for more convenient to identify this is an air inlet, so we change the name to air inlet. And then we fill in the value as per the question. So the velocity magnitude for air inlet is 0.5 meter per second. So if you can view back here, 0.5 meter per second. Temperature is 300 K, so 0.5. And then the turbulent intensity will be 10. Before you further define, make sure you go to specification method here. We're going to use intensity and hydraulic diameter. So you look at the diameter there. So you look at this diagram. So the diameter here to here is 0.0025. For air, it's only this section to this section. So 0.225 minus 0.005, you get 0.002 is your radius, right? It's your radius. But the software asks for diameter, so the answer here is 0.44. Yeah. 0.44. Then after that, you go to thermal just to check the input is correct. It's 300 is correct. Yeah. So then after that, we go to species here. So species there, we will define species here. It will be oxygen. So oxygen, the mass fraction here will be 0.23. Okay, 0.23. So the value that we use in this in all these setting is referring to experimental data, which is defined in. Let me find the reference for you. Let me put it somewhere. It's defined by an experiment data by let me check for you. By referring to the stoichiometric table. But in this case, we will use the value at the moment. So the value here is 0.23, is 23% of our inlet. So, okay. All right, so this one, we assume that we have this one. And again, all this number is referring to an experimental data, or there's a diagram or table for you to fill in. Yeah. So during your assignment or test, all this number will be given in a table. You need to put inside this one. Yeah. So for the industry application, you need to check from your chemist. There's a table in the experiment, in the sampling. There's a mass fraction from their experiment. You get this value from the lab. Huh? So after that, we have defined for our air inlet. Then we'll click OK. We'll define for our air inlet already. The next step is that we'll define for our fuel inlet, which is here, this small function here. We define a parameter for our fuel inlet, it is here, from the methane, 80 meter per second, 300K. And our diameter will be 0.005 times 2 will be 0.01 later on in our setting. Okay, back to here. Fuel here, the ID here is ID number 6 here. So ID number 6. So you go to edit. Again, how you know it's ID 6, you go here, right click, you'll see the ID will come up, like what I showed you 5 to 10 minutes ago. Yeah. Go back to the video if you want to. Okay, we rename this one as fuel inlet here, just to have more clarification. The magnitude of velocity will be 80. Turbulence intensity will put to 10. Again, change the turbulence specification method to hydraulic diameter. And the diameter here will be 0.01, okay, referring to the diagram. It is this one. Yeah. So this is radius. So you need to key in diameter, so times 2. This value times 2, you get diameter. After that, you go to thermal, check the temperature. The temperature will be 300K. And then you go to species, and at your fuel inlet there, your species is CO4, right? So CO4 is 100%, so put in 1. Yeah, put in 1. So just now you input the oxygen in the air will be 23% of in the atmospheric. Your oxygen will be 23%. So that's why you put a 0.23 just now. Yeah. So in this case, for fuel inlet, you have 100% of methane. So you put 1 over there. The rest is 0. So after that, we'll click OK. We have our fuel inlet already. The next one, we will define our pressure outlet. So our pressure outlet is number 9 here. So click number 9, pressure outlet number 9, click edit. We will input for, so for momentum, gauge pressure will be 0 at this side. And then you go to turbulence, specific method again, we go to diameter. Intensity we set to 10, and the diameter will be 0.45. You should be able to understand why the diameter is 0.45. I will show you. So over here, yeah. So if you, this is a radius, so you times 2, you'll get 0.45. Okay. So after that, in the thermal, this one. So the thermal backflow total temperature, we will set as 300. Yeah. So as you can see here, we will follow the temperature. Okay. And the species here, our oxygen in the atmosphere is 23%, so 0.23 on this side, exposed to atmospheric. So oxygen mass fraction is 0.23. All right, after that, for pressure outlet is done, so click OK. Then we need to define for our wall number 7, number 2 here. So we go to number 7 first. So number 7, we go to edit. So number 7 here is referring to outer wall. So we changed it to outer wall, or any name that you feel comfortable with. This one refer to outer wall. So outer wall, we will control the thermal. So in momentum here is stationary wall, no slip and all this. The wall is not moving. And then the thermal here, we will make sure that there is no heat transfer happening. So full insulation, so heat flux will be 0. No, for wall, sorry, go back to the diagram. So the wall here is, we have a temperature, our wall is 300K. So we have to change the setting to 300K. It's not heat flux. We go to temperature and it's 300. Yeah, make sure here. We do exactly to the diagram there. And then click OK. So we're done for outer wall. And then we have wall number 2 is our for our fuel inlet nozzle. Okay, it is here, right? Fuel inlet nozzle over here, right? So go to wall 2, edit. So for our wall, just name this one as our nozzle because we're defining nozzle. And then the thermal, we will, for nozzle there's no heat transfer happening. So heat flux here, we retain as 0 for our nozzle area. After that, click OK. So we have done setting for all our boundary condition. So from just now, we already changed the name and also we input some parameter according to this diagram. All right. So we have done boundary condition. After that, we will go for our reaction solution. So in this case, we will first calculate the solution for the basic reacting flow by ignoring the pollutant formation. So the first case we are running here will be ignoring the pollutant formation with this NOx, the pollutant formation. So after we get one cycle of the results, then later we'll perform additional analysis for the pollutant formation, which is your NOx pollutant. Okay, so in this case, we're going to method, solution, method. Yeah, you can double click method, or you can go to solving, then go to method. You click method, you will see this one. So in this case, we will activate for our pressure velocity coupling here. We will use coupled scheme. And then we will We will use back the least square cell base for special discretization. And in this case, we will activate the pseudo transient calculation. Now, again, pseudo transient, what does it do? If you enable the pseudo transient, it's going to activate or add in a pseudo transient algorithm into the coupled partial velocity coupling solution method here, so that the algorithm, the combination of pseudo transient and the coupled scheme equation, the combination of this one plus this one, it will help the equation to solve in a faster way to improve the stability and convergent behavior. In short, means that you're able to reach convergence faster. Then after that, we're going to control. After you define your solution method, you go to control, double click control. And in this case, we will reduce the density, the effect of our density over here. We will reduce it from 1 to 0.25. Okay. Yeah, so you can come back to this control for your relationship factor if you're not able to reach the convergence, right? You just come here and reduce the numbers accordingly. And after that, we will click the advanced button here. So we will go to advanced solution control here. And we will go to expert tab here. So in expert tab here, what you will see a spatial desiccation limiter, and you will see the pseudo transient method for your kinetic energy, dissipation rate, energy, and you see that the species is over here, right? The species is over here. We're going to activate the solution to calculate our methane, CO4, CH4, oxygen, carbon dioxide, and water. So make sure you select this one. And then the time scale here, we will increase to 10 for all the species, chemical species that you have there, including your energy in the calculation. All right. Then after that, we will click OK in the expert tab here. Click OK. After done with your solution control, we will ensure that we are plotting residuals during the calculation. So residual will help us to see the activity in our simulation. So we need to activate the residuals. So where is residual is under solving, reports residuals. So just open up the residuals. You go to solving, reports residuals, and then make sure you have tick the plot here so that later on the plot will come out. And then our convergent criteria is given here. What is important is that you make sure that make sure you activate the plot here. Right, then click OK. Then we will initialize the field variable that we just set up just now. Because just now we set up the boundary condition, the velocity, the temperature, so we need to use all the parameter to set our calculation. So you go to initialization. There's a hybrid initialization. We need to initiate the hybrid. So once you click this one, something will happen to the console. Click initiate. So it will tell you that hybrid initialization is done, which is okay. And you'll see that your max fraction for your species is coming out here. All right. Now, after you've done the initialization for hybrid, to secure your file, it's always advise you to save the file of your case and data. In this case, I will just save my case. So I go to my file, just save my file as gas combustion number 1 .cas.gz. Again, .cas.gz. The term here .gz means you ask the computer to compress the data for you. Without .gz, you will have the raw file. Sometimes it will be very big. So it's always recommended to use .gz in your simulation. This is the first case. We'll include everything in the combustion. Then click OK. So you will save the setting and the data. So after that, we will okay. Before that, just now when you export, right? When you export the case file, make sure that you activate the write and binding files. Yeah, make sure you tick this one. All right. Then after that, we're going to run the iteration for 200 iteration. So you go to run calculation advanced here. We're going to change this one to 200 iteration. And also we will change the length scale method from conservative to aggressive. Right, the length scale method we changed for conservative to aggressive. Now, why we change to aggressive? So when we use the automatic steps, when you use the automatic automatic steps, time step method, it will compute the pseudo transient time steps based on characteristic length and velocity scale of the problems. You will look at characteristic length and velocity scale. And the conservative length scale method use a smaller of 2 compute length scale emphasize solution stability. The aggressive length scale method, where we chosen now, the aggressive method use a larger of 2, which may provide a faster conversion in some case. So in this case, we choose aggressive that it might help us to reach conversion in faster pace. So later you'll see when you click calculate, it will calculate faster than the common one, right? Then after that, we will time scale factor, we will increase it to 5. Yeah. So this time scale factor, what does it do? It will allow you to further manipulate and the compute time step calculated in the ANSYS software. The larger time step that we include here will lead to a faster conversion. However, if the time step is too large, it can lead to instability in your solution. So you need to be comfortable with the value over here. In this case, we'll increase to 5. Then make sure that you include 200 number iteration for this case first, and then you click calculate. So you see that the activity is very fast compared to the conventional one. All right, so you say calculation completed, and this is what we want, yeah. So the solution is converged at 155 convergent, yeah, 115 convergence. It already converged. All right, so we're going. Once we have a calculation, we want to export our case and data just for our record, yeah. So save somewhere. And this one is gas combustion case 1.cas.gz. Again, we use .gz to compress our data file. After that, we are done. We're going to project our result. So we go to post-processing. The first case is that we want to see our heat flux data. So we're going to report, go to report, and then we go to flux, post-processing, report flux, and then the computer will ask you what report you want to see. In this case, we're going to see the third one, the total sensible heat transfer rate in this case, and then we're going to see all the boundaries that we set here. Select all to ask the computer to compute for you. Then we click compute. So in this case, you will see that the important is to make sure this net result is smaller compared to this number. And you can compare to all this also. Make sure this number is smaller than what you see on the results over here. Okay. We call it this net result. We call it energy balance, and we consider it's a good energy balance is achieved in this case because the net results here is small compared to the reaction. The heat of reaction source here is very small. Yeah, very small. Okay, now this is how you get the value for your heat reaction source in watt. You have a 203,633 watt. And then for air inlet, there is a heat transfer rate. Air inlet happened in 173 watt, and so on. Fuel inlet, there's 16 watt. For outer wall, you have 11,787 watt. And for pressure outlet, you have this number, okay? Right, so this is how you call all the value. So in test or ANSYS or your assignment, you need to copy this number and paste in the answer sheet. Huh? Okay, close. After that, after we read the data for our heat flux, after that we will see the control of temperature, which is very important for combustion analysis. So we see the temperature first. So how do you call out the contour? Again, go to processing, graphic, you go to contour and edit. So this window will come out. So it asks you what you want to project for contour. So in this case, we will click the fill. You'll fill the graph with the color, and we are going to see temperature. So select temperature, static temperature, and we will displace. So if you don't see anything, don't panic. Just go here and click zoom fit, and you can move and then you use your mouse to orientate the graph. So what we see here is that the temperature, the maximum temperature here is 231 Kelvin, which happened over here. The temperature contour in the combustion process. The maximum temperature we have is 231 Kelvin. Minimum is 300 Kelvin. Okay. Yeah, so this is what you can conclude from the contour for temperature. After that, you close this one, and sometimes you need to extract this photo. So what you need to do is you go to save picture here and save and rename, and you can preview also to save the picture. Yeah, close. After that, we're going to see the velocity vector. That we see how fast our molecule is moving inside the combustor. So we want to use vector to project velocity. So go to processing, graphic, vector, and then we go to edit. So again, the window come out will ask you what you want to simulate or what you want to project. So we want to project velocity, vector, and the arrow here we will scale down. Yeah, we will scale down to 0.01. So and then we're going to click the vector option. We further define our vector presentation. So if you have a vector option open up, we're going to have a fixed length in our presentation. So you click fixed length. So later on, I'll explain what is fixed length about. So click fixed length. Then click apply. Apply, close. And then after that, you click display. So this is the presentation when you click activate the fixed length. If you zoom in, you'll see that the fixed length option is very useful when the vector magnitude varies dramatically, where you can see that there's a mixture of the let me close this one. You can see that the vector length here is same, although the color is changing. So by fixing the vector length will help you to have a better understanding of the vector with some distance from the left to right. And by looking at the color, you will see that what happened to the velocity inside the system. So in this case, what you have is that you have a maximum velocity in your methane inlet over here. The maximum, it can go up to 82.3 meter per second over here. The minimum is 0.4 meter per second, which is for the air here. Then after the mixing, the mixing of the methane and air, something will happen to the velocity over here. So this is how we do setting for the vector, velocity vector. The next one we're going to do, we're going to look at our stream function. Our stream function. So stream function also important when you study fluid mechanics. So how do you project the contour of stream function? So again, you go to post-processing, you go to contour here again, contour edit, and then under contour, we're going to see stream function. So drop down and find stream function. Oops. Under contour, or velocity, sorry, under velocity, you go to the second one, there's a stream function here. Velocity, then go to select stream function, then click display. So this is your stream function in kilogram per second. So maximum is 155, no, negative 2 is 0.01 kilogram per second happen in here. The smallest one will be negative 19 over here. Okay, so this is how you explain about the graph. And you can, again, you can move the graph to one side and then minimize it with your mouse. Yeah, and then you capture this photo, put in the report or in your answer sheet. So this is how we project the stream function. The next one, we're going to look at our species, which is the combustion products. Again, we have 4 species of products that we're going to look at. The first one, we look at our methane. So we close this one. We're going to look at a graphic represent our mass function. So go to post-processing, contour again, and then edit. So in this case, we're going to look at our mass fraction. So we're going to focus on our species, which is a combustion process products. Species, and then the first one you can choose is, there are many you can choose here. Yeah, the first one you look at is our methane. We're going to look at mass fraction of CH4 with our methane. Then you click display. So you can see here our mass fraction 1. If we zoom in, so it's agreed that we have 100% of methane over here, and it start mixing in this region. The mass fraction reduce as it go further. Right, as you go further, it will mix with air itself. So this is how you explain about this diagram over here. So after that, we see the mass fraction of CH4. You can look for, if you want to look at oxygen, so you select oxygen and display. So you can see that is agree with the normal case. You can see here, this is a methane inlet, your methane inlet, and then this is the, on top of the inlet here is your oxygen or normal air, which is 23% from the atmospheric. Yeah, so you will see that the mass fraction here is 0.23% of oxygen, and then it start mixing when it get contact with the methane over here. Right, this is for when you generate report or answer for the test, you just fit the window and then you move the graph to one side. Use your mouse to minimize it. So you will see this graph, you can just capture a print screen and then put into the answer sheet there. All right, so we have shown you how to show the mass fraction for CO2. You can do for CO2 also. Select CO2, click display. So this is your CO2. You can see the maximum CO2 products will be happening here. Minimum will be here because this is your inlet, which is logic to happen. The oxygen is over here, and then there's a mixing, combustion happen, and then you have a CO2 in 0.146% in this region over here. Okay, so this is how you see the CO2 mass fraction. And you can see for water also, because you generate water in the chemical products or in a combustion. So you can go and select water and click display. So you'll see that the maximum of water generated in the combustion will be this region. Same with the CO2. The percentage is very small. Yeah, the water is very small. Is 0.01%. 0.01% of the total mass that you have here. You have water over here. Okay, so from these three graph, from these three contour, you can see the percentage of the combustion process. All right, so you close this one. The next one, you can also see the average exit temperature. So you can go to post-processing. You go to report and you go to surface integral. So under surface integral, you want to look for mass, report type in the mass weighted average. And we want to look for temperature. So what we're going to do is that we ask the computer to compute the average exit temperature at over here. So when you select the surface there, select outlet. So you make the computer to calculate the temperature in the outlet over here. That's why you select pressure outlet number 9. And then the report type is based on mass weight average. And you press compute. Yeah. The average match average will be 1839 Kelvin. Will be about 1840 Kelvin happening over here. Yeah. So there is a formula that could calculate this temperature. It's given by this formula. Let me show you. I have it in my slides. Okay, by this formula, yeah, by the average mass average temperature given by integration of this portion divided by this portion. All right. We back to the ANSYS itself. Then after that, we have seen the temperature already. We will look at what about the velocity. So we ask the computer to compute the velocity for us. So just now we calculate temperature. Now we calculate the velocity at outlet here. What is the velocity that at here? So select pressure outlet number 9, press compute. So the speed at the outlet there will be 3.42 about this value. About this value. So after that, for velocity, we're going to use the not mass weighted. It will be area weighted average. For velocity magnitude, we use area weighted average. So click this one. We click compute. All right. So the velocity under the report type area weighted average, we will get 3.3. Yeah. For velocity, we use area weight. For temperature, we use mass weight. Yeah. Again, for temperature, we use mass weighted average if you want to see temperature. Yeah, at outlet here. So if you want to calculate the value for velocity, we will choose area weighted average. Okay, you get 3.3 meter per second over here. So just take note on the report type. Yeah, area weighted average for velocity, mass weighted is for temperature. Okay, So we have done for the normal simulation, including all the species, including all the species. Now, what about if you want to simulate the pollutant, the pollutant in the process? Pollutant means the side products of the combustion. Yeah. So pollutant in the chemical terms is NOx. NOx represent our pollutant. So we're going to do two steps over here. The first one we're going to do to include the prediction of NOx, which is include the pollutant in our calculation. There are two types of pollutant. One is thermal NOx and also prom NOx. So we will include this both first, and then later we will see the differences if we go for individual pollutant calculation. All right, so how do we include the pollutant in our calculation? So you go to model here, go to species, under species. You can see here just now we do not on the NOx. This is the pollutant calculation. So we're going to on this NOx here, edit. So inside for NOx model, NOx means pollutant model. So in the first scenario, we're going to look at thermal NOx and prom NOx. We're going to look at these two. Then later we look at individual cases where we will only consider thermal NOx or prom NOx. So in this case, now we're going to simulate the combustion process with the pollutant. The previous simulation steps that I show you is without pollutant. Now what we're going to do is we're going to activate the calculation including the pollutant, which is NOx. So in this case, we select thermal NOx and prom NOx. And then for our fuel species is from the methane, means the side products of combustion from the methane itself. We will be considering the thermal and the prom NOx here. Then after that, we will, after you select thermal and prom and go select your methane fuel species, you go to turbulent interaction mode here, where you can change the PDF mode. Now, more detail on a PDF, you can go and Google and find more information about PDF mode. And then you drop down PDF mode. We're going to use PDF mode, temperature mode. Okay. Now this will enable what does it do to your calculation? If you enable the temperature PDF mode, it will enable the turbulent chemistry interaction to happen. If you activate temperature in the turbulent interaction mode, if you activate temperature, it will enable the chemistry to happen. And then if the turbulence interaction is not enabled, you will be computing the pollutant formation without considering the important influence of turbulence fluctuation in the time average reaction. So if you do not activate this one, means that you do not consider the turbulent interaction. Yeah. So in this case, we will consider the turbulent interaction in this case. So we activate the temperature. Then after that, we will use the beta information. The PDF point will increase to 20. Just go up to 20. Increase the PDF point. The higher value you increase it will give you more accurate of your pollutant prediction. Yeah, the higher, the maximum. Yeah, I mean the value we increase is to increase the accuracy of our pollutant NOx pollutant prediction. Then after that, we will, for the temperature variance here, we will change the algebraic to transported. So our pollutant is transported in a temperature. Okay, then you go to your oxygen model here. So oxygen model here, we will use partial equilibrium. Yeah, partial equilibrium, what does it do? It will predict the oxygen or the O radical concentration required for the thermal NOx prediction. Meaning partial equilibrium means we will see more side products of the chemical combustion, right? The equilibrium of the combustion process, right? Then after that, we go to, this is for the thermal. We will consider the thermal and prom for the NOx. For thermal, we will change the oxygen to partial equilibrium. Go to prom thermal here. We're going to equilibrium ratio here. We will drop to 0.76 here. All right. So what does this number meaning? It means that the carbon, the fuel carbon number. What is fuel carbon number? Fuel carbon number is a number of carbon carbon atom per molecule. Mean means one carbon in the molecule. Right? The equivalent ratio, it is here. It defines this one, the value over here. It defines the fuel air ratio, fuel to air ratio. So we have a 76%, 0.76 here. So if you go to the statement of the scenario that we have, so we have overall equivalent 0.76. So this is the statement, the information we use over here. So that's why the value we use 0.76 here for prom nitrox, not nitrox, prom pollutant model. Okay, 0.76 here. Then after that, we will apply to accept all the changes, then close it. Then after that, we will enable the calculation of the NO species only and the temperature variance. So how we only enable the calculation for NO species and temperature variance only? We go to solving, and then we go to control, and then there's an equation there. Okay, solving control equation. So you can see by default the equation consider all these input, but in this case we only consider only the pollutant and the temperature variance only. Okay, we only consider these two equations. All right, so these are the two focus that we're focusing on. So that's why you select these two. This one will be calculated in the post-processing mode. What else? So in this case, only the NO equation will be computed if you only select this one. Right, so then click OK. Then after that, we go to control, solving, we go to control over here, or you can go to solution, control, you'll still reach the same page here. So in this case, we go to advanced. Okay, again, solving, control, you go to the relaxation factor page, go to advanced. Then after that, in the expert tab here, you will go to we are going to enable our method, we're going to enable pollutant number and pollutant NO, not number. Our pollutant nitrogen, oxygen, mononitrate, right? Means one molecule, one nitrate plus one oxygen atom, pollutant NO. Yeah? So you're going to activate pollutant and temperature variance. And then we're going to increase these two into 10, 10, yeah? So we're going to increase the pollutant and temperature variance. After that, click OK. Okay, then we go to, in this pseudo transient relaxation factor here, you drop down, you're going to see these two pollutant of nitrogen, mononitrogen, or NO, nitrogen oxygen. We're going to increase this one to 1, that way we'll focus on these two. Temperature variance also increase to 1, where we will focus on these two factor in our calculation. So increase pollutant nitrogen oxygen to 1, temperature variance to 1. After that, we're going to confirm the conversion criteria. So we go to solving, report residuals. So just this is to check our residual monitor. Make sure that we are running our residual monitor. What you need to be careful is that trying to make sure that you have a very small absolute criteria for your convergence. Yeah, your convergence, you set the computer to monitor at 1 10 power negative 6 absolute value. Yeah, which is quite a good convergence criteria to set to monitor. Okay. After that, click OK. Then we'll run the iteration. So go to solving, advanced, and then in this case we don't need so many. We just run 25 iteration. So you'll see that the calculation will continue for another 25 iteration. Then we'll run calculate. Okay. So you see complete, and it reached conversion in just now 155 to 165 is about 15 iteration here. Okay, about no, it's about 10. 155 is the previous one. 165 is the current one. So 155 to 161 is 10 iteration. So your solution reach in 10 resolution. Okay, once we run the iteration, we have the result already. I will export my case and data to my folder. We're going to rename this data to a second data, gas combustion number 2.cas.gz. So again, .gz is to zip the file. Just now, the combustion 1 is the normal combustion process without the pollutant. And we already come to the simulation where we simulate the pollutant. Right? We simulate the pollutant where we label as number 2. Okay. Now we see what is the results, yeah, for comparison when we include the pollutant products. So we go to the first thing, we look at the NO mass fraction. So post-processing, graphic, contour, edit, and in this case, we will we want to save this contour to this window, so go again. Post-processing, contour, we go to new, so later you come out in this window. The contour name will be contour NO, nitrogen oxygen mass fraction graph. And then we don't want to see the fill contour, And then we'll select species from, we'll select the mass, we select the NOx, the pollutant, from the mass fraction pollutant NO. Okay, contour of our pollutant under mass fraction of pollutant number over here, and then we display. So as you can see here, what this graph represent, you ask the computer to project a contour without filling in the color. So based on all this line, you will see that the maximum mass fraction for your pollutant is happening on the right hand side of the combustion process. So again, your air come in left hand side, your fuel come in right hand side, something mixing inside there, the maximum pollutant that you have. The pollutant you are looking at is nitrogen oxygen pollutant, maximum accumulate in this section. All right, red color. And the value you can read from here. All right. Okay, so this is how you project the pollutant for nitrogen oxygen in the mass fraction. So we close it. The next one, we're going to ask the computer to give us the value of average acid of our nitrogen oxygen mass fraction. So post-processing, go to report and surface interval. Again, every time you want to ask the computer to give you some value, you go to post-processing, report, and it depends on what area you want to see. In this one, we go to see surface integral. And for NOx, we will look for mass, not area, we'll go for mass average weight. Going to look at pollutant, NOx. And then this one, mass fraction of pollutant number. We're going to look at pressure outlet number 9. Okay, pressure outlet number 9 over here. Okay, we want to look at what is the value of our pollutant. So compute. You will see that our mesh average over here will be very small, 0.004. Yeah, will be 0.004. This is our pollutant mass fraction at this one will be 0.004% of 0.004% is your pollutant NOx here. Okay. Close this one. Now the next step, we're going to look at, in this case, we already look at two types of pollutant. Again, we look at prom and thermal. Now, what happens if you only consider one of the type of the NOx? So we go to setup here again. Model, species transport, NOx on. We go to edit. So you go to formation. So again, just now what the data we show is two types of NOx or pollutant. Now we look at thermal NOx only. So we disable this one. So we look at thermal NOx only. Then we click apply. Close. So now we only look at thermal, and then we run the simulation again. Go to solving, advanced, run calculation, advanced, and then we run 25 iteration again and calculate. Complete, and then you go in console here, check that is already converged. So just now we converged at 165. 165 to 171 is about 6 iteration. Yeah. So it reached convergence in 6 iteration. All right. Now again, this case is we're looking at the thermal NOx. So we look at the data. So to present data, we go to the result here on the tree here, result, graphic. There's a contour there. So under contour mass, this one, you go a left click, a right click, and then click display. So this is the mass fraction of NOx when we consider the thermal NOx only. So you can print screen this one and then make comparison with the previous one. Yeah. Okay. Now you can save this photo to make comparison. Yeah. So the next one we consider for prom NOx only. So again, you go back to the model, go to species, NOx, go and edit this one. We're going to activate the prom and then deactivate thermal to study about this one. Apply, close, and then we run the calculation again. Solving, advanced, and then run for 25 iteration again. So you see the convergence reached 184. The previous one is 171. So 171 to 184 is about 13 steps. So the solution reached convergence in 13 iteration. So this solution is only consider the prom NOx action only. So we can display the same results. So you go to result here, 3 results, contour mass fraction, and we can click display. Then you can capture this photo. As you can see, the number dropped a little bit if we only consider the prom NOx only. So you can compare between the previous one and this one. You can put side by side, and then you can see the differences. Okay? For the NOx species, NO species, yeah, NO species. Okay. Now the next step is that we want to compute. Again, ask the computer to give you some value about something. So you go to post-processing, a report. We're going to surface interval again to ask the computer to compute for us on the average acid. Yeah? Average acid. So let's go here and mass weighted average for the report type. And then we're going to look at NOx, at pressure. So compute. So you see the value is very small. It's 9.9 10 power negative 5 for your pollutant at pressure at this section here. All right, and it's only is under the consideration of the setting that you did just now, where you only consider the prom NOx setting. All right. You can use a custom field to calculate the NOx part per million. It's given by this formula. So let me show you the formula in my PowerPoint slides. Okay. It's governed by this equation later on. So later we're going to pull out the calculator to put in this formula. So I'm going to show you how, and you can write this formula in your notes there, and then later you can follow what we can do with the calculator, right? So to calculate the number of parts per million, or ppm, number of parts per million, we take number of mole, NO, nitrogen, oxygen, mole fraction times 10 power 6 divided by 1 minus oxygen, not oxygen, water, H2O mole per fraction. So you take mole per fraction for your NO, mononitrate, right? So NO divided by the water, 1 minus water mole fraction. So how do we put all this number into this calculator? So I'm going to show you how to do the manual calculation. So you go to the top here. There's a ribbon called user define, and then there's a custom. So click the custom. So the calculator will come up. Again, to the first number we want to calculate is our NO mole fraction number. So NO mole fraction number, we ask the computer to get it for us. So you go to species, and then look for your NO. Yeah, look for NO. Sorry, NOx. You look for this is NOx pollutant. Okay. So this is your NO mole fraction, is your pollutant. So we will select NOx pollutant under mass fraction pollutant number. Once you click select, you will put into the calculator. Okay, click select. You will see MF pollutant 0 here. And then because our equation is 10 power 6, so we go to calculator here, times 10 power 6, and then you divide by 1 minus water. So we have to divide, and then use the bracket or column 1 minus, and then the water. So how do you find water? So the water is under species, and then there is water there, mole fraction of water. Not mass fraction, it's a mole fraction. Mole fraction of water. Select. Then remember to close the equation, if not you'll come error. We need to make sure that the definition or the calculation or programming language we use here is complete. Close the programming here. All right. Then the new function here, we will chain it to number of ppm. So this one will let us to reuse this formula again and again. So we save this formula as number of ppm. All right. Then we click define. Then we click close. So after that, we will ask the computer to show the contour based on the formula that we put in. So you go to post-processing, and graphic, contour, and then edit. So just now we key in one formula, which is the number of ppm. So you go to number of ppm. So go to contour of custom field function, number of ppm. Then you click display. So this is the number of ppm inside the contour of nitrox NO, nitrogen oxygen ppm. Yeah, parts per minute. So it means that you have how many atoms of or molecule of nitrogen oxygen in a million. All right. So the maximum number here will be 154 over million, 154 atom or molecule of nitrogen oxygen in this region per million over here. Okay, maximum NO will be here. The number of nitrogen oxygen molecule per million will be 154 per million ppm in this region. Okay, 154 ppm in this region. Minimum is 0 over here. Okay, so this is how you calculate or project the contour of ppm. An element, in this case, we look at nitrogen oxygen molecule. per million, part per million, according to the equation that we just key in, right? According to this equation. All right. So, okay, in this case, maybe you have full of color, you can deselect the field and then display. You'll see that it's only project in the line where you'll see only contour with the line, but it will be the same information where you'll see the maximum is over here for nitrogen, oxygen per part per million will be here. You have 154 molecule of nitrogen, oxygen per million in this region. And there's no nitrogen, oxygen in this region. Okay. So with this, I end the recording for simulating the species transport and gas combustion. So let me end the recording.